This is the 11.8 overview for Math222, that's Calc 2. 11.8 is power series. Okay, so if you have anything of this format, it's called a power series, where you have constants, x to the n, whatever your independent variable is. So this guy is your variable, and this guy is essentially a sequence of coefficients. Okay, this is power series. So it looks just like a polynomial, but it is allowed to go on forever. So if you have a polynomial, it's automatically a power series. Okay, the only difference is the polynomial chops off the last infinity number of terms, whereas the power series goes on forever. Kind of like if you have a repeating decimal, it is a decimal, but it's also a rational number. So the all rational numbers are decimals, but all rational numbers are real, okay, but not all real numbers are rational. Same kind of relationship. So if you have the coefficient sequence and it looks like this, for example, 1, 2, 3, and the rest of them are zeros, then you can just apply them and get polynomial 1 plus 2x plus 3x squared, and there's no need to continue because the rest of them are 0. Okay, so that's the first idea. A non-terminating example is something very similar to what we've been doing. It's just the same old geometric thing that we've been dealing with, but I'm going to use x's instead of r's. And you may say, well, what's the difference between x's and r's? Well, it's the same difference we had in high school when you had something like y equals ax squared plus bx plus c, right? You had a different relationship. The a, b, and c held a different role than the x or even the y. So it's that kind of thing. It's not profoundly different. It's just a difference in how we use it. So we solve this. We use, if we use s to represent the sum, remember we did this already, x times s is going to bump up the powers on all these guys. So what happens if we take s minus x times s? Well, we're going to get rid of all these guys on and on forever, and then we're going to end up with just 1. They just solve for s. Okay, it's just that simple, but of course the magnitude of x has to be less than 1 or else this is ridiculous. Okay? So that was the second concept. Right, now you could imagine, just like we did this in high school, a, b, and c are somehow more solid than x is. So that was the point I was making before. Okay, we can shift these guys. Okay, shifting power series. This can be shifted, but you have to deal with the algebra. So for example, we just want a different, we're shifting the origin in a sense, the center. We call it the center, but it's the role that the origin often plays. We now call this centered. This is a power series centered at A, or about A, or centered about A. Those are all different ways of saying the same thing. So, example. Write this normal polynomial, just a parabola, as a power series centered at 4. Okay, so this one is just algebra, and later we'll do this without using the algebra, using a different trick. But we just know f is equal to something times x minus 4 squared plus something times x minus 4 plus something. And we just have to find out what those somethings are. So first of all, we have to have 3 initially, right? And then maybe a and b. one way to think of it. We know it has to be 3, otherwise we're not going to match this x squared. So there's no sense guessing that has to be the case. So let's figure out what's going on. We square this, x squared minus 8x plus 16. Then 3x squared is already matching up. Okay, so we can get rid of 3x squared. But we don't really want to get rid of the 3. Minus 24x, 48, plus ax minus 4a plus b is 2x, whoops, negative 2x plus 7. So the next thing we have to match up is the x's, so negative 24x plus ax equals negative 2. So that means negative 24 plus a equals negative 2. I'm going to add 24 to both sides. Okay, so now I know that this guy has to be a 22. Alright? Now what? Well, if that has to be a 22, then we can go back and figure out more, right? We can go back and figure out if this is now a 22, then we can get rid of this. We could try this again. So we don't have to worry about making the x's match up, and we don't have to worry about making the x squareds match up, because those are they're all gone now. This is gone, this is gone, this is gone. But now we're worried about this guy. We're worried about the b. So 3 times 16, 48, plus 22b is equal to 7. So we have okay, I gotta get my algebra straight, sorry about that. Alright, so 22 minus 4 is minus 88, of course. And so we have minus 40 plus b is 7. B is going to add 40 to both sides. Okay, so now this should be 47. I'm going to get rid of this, which I don't feel bad about, because you can back up the video if you want. Okay, there we go. So now we found our coefficients. No big deal. So this guy here is a power series about 4, and this guy's is just a power series about 0. And they represent the same function. Okay, next question. Is this guy ever convergent? This is a factorial. Alright, I mean, think about it. We don't really care about where we're starting as long as it's not at nowhere. Okay, so this guy is only convergent at x equals 0. It's kind of obvious. And you can use the ratio test to prove it, that unless you put in 0, this thing just grows really, really fast. So why is this example even important? Well, because it's one of the 3 cases we're going to talk about. There's only 3 things that these power series can do. They're either going to converge everywhere, or they're going to converge on a certain interval, which is the center of the interval has to be the center of the series, which is kind of cool. And then we could perhaps converge at just the center. Those are the only 3 options. So this is given as an example, and it may seem stupid, but it's just given as an example of what can happen. Alright, what about this guy? Does this guy converge? Let's see. N is equal to, who cares? I don't care where it starts. As long as it doesn't cause any division by 0 or anything weird to happen. And this one is not obvious, so let's go ahead and use, well, maybe it's obvious, but we can go ahead and use the ratio test. I would really love an abbreviation for ratio test, but if I did RT, it would look like root test. Okay, limit as n goes to infinity. Okay, so what I'm going to do is I'm going to actually shortcut this algebra. See how there's an n? Well, that means I'm going to end up with an n plus 1 on the top, because if I put an n on the bottom, okay? But I'm not going to write out all the terms. X minus 3 to the power of n plus 1 is going to go on top, and to the power of n is going to go on the bottom. So I'm just going to end up with a single solitary x minus 3, okay? As n goes to infinity, this piece goes to 1. And, okay, that's sloppy. What would I expect you to do on an exam? Goes to 1 is fine. So the thing is, you could technically write this as, put this limit sign and then put the first piece down with the absolute value sign, and then times the limit sign times the second piece. And I don't expect you to waste your time to do that during an exam. You're not publishing a paper, so I mean, if you do publish a paper, write it all out perfectly. And so limit as n goes to infinity of x minus 3 with absolute value signs is still just x minus 3. And so we know this guy, because of the fact that we're using the ratio test, this less than 1, this piece and this whole structure, it came from the ratio test. That's why we're using it. Okay, then we can continue on and say x minus 3 is sandwiched between 1 and negative 1. We just removed the absolute value sign, so we're going on either side now. We're going to add 3 to all sides. And the question is, I put little question marks because we don't know about the endpoint, so we have to think this through. If we put x is 4 in here, what's going to happen? What we're going to have is 1 over n. So it's going to be the harmonic series. So this guy does not converge. But if we put 2 in here, we get negative 1. So it's going to conditionally converge. Okay? And there you go. And that will be how we figure that out. So beware the alternating series, especially harmonic and alternating harmonic series. They come up a lot in these questions. They're just on the edges, just the very edges. That doesn't apply, you know, when we talk about later how we, you know, the center and the radius of convergence come along for the ride whenever we differentiate and integrate, but the edges don't. We have to check the edges each time. So sorry about that. And that's the way it goes. And I just did want to mention that the reason we call these radius of convergence and so forth, in the real, in the complex world, it's really a circle. So just so you know, it's not just a circle of convergence or radius of convergence. All this terminology about circles, these things just carry over. Okay, we have page 743, a theorem which says that this guy, you pop down any C's you want. Alright, there's only 3 options. It converge at x equals a. I mean, that's kind of dumb, right? Because it's all going to be, well, all you're going to get is one constant. So, I mean, that constant you can have. Go ahead and take it. Or you can converge for all x. Okay, that's not exciting. We can converge. The other option is x minus a is within a radius, but this guy is guaranteed to diverge. That's what makes it super cool, because everything inside the circle is good, everything outside the circle is bad, and there's no exceptions. The only little thing you have to worry about again is that whole boundary. The boundary you have to test each time, and because we're only in one dimension, we don't worry about anything except 2 little teeny little points. Okay, and in complex analysis we get to do this cool thing called Laurent series, where it's the exact opposite. The Laurent series is just flipped. It's inside out. So then the divergence is inside the circle and the convergence is outside the circle. But we're not doing that in this case, in this course. Okay? There's a couple things from the book that I'm going to pass over for this video. We did find the domain of the Bessel function. That is in the textbook, and I don't think you will get a tremendous benefit from me putting it on the video, because I don't have much to say except what the textbook says. Let's see. Alright, I'll give you one more example of the convergence of this guy. So when does it converge? Well, we're going to use the ratio test. And you know what? If you write the word ratio test, that's fine. You don't have to then write this mess. Okay, so you can do it either way. You can write out the formula, or you can just tell me you're using the ratio test. As long as you, that to me is showing work. Because I understand that your time is limited on an exam. That's totally fine with me. Okay, so if you have the negative 3 to the n, you're going to have negative 3 to the n downstairs and negative 3 to the n plus 1 upstairs. So what are you going to end up with? You're going to end up with just a 3, because this thing is in absolute values anyway. What about x? The x piece has the same property. You're going to end up with x to the n in the bottom, x to the n plus 1 upstairs, and so that's going to give you just an x upstairs. And then what? Well, you're going to get square root of, and I'm just going to do this to remind you what's going on. That's going to cancel, that's going to go to 1, and then so we need this guy, the 3x has to be less than 1, so the center is at 0, radius is 1/3. We still don't know about the endpoints. It will turn out that 1 converges and 1 diverges. I'll let you look into that. And one more point I wanted to make about this. Note, this is going to be a recurring theme in some of our questions as we study for the exam. If we have something like this, n squared plus 4n plus 4, I'm going to make it really, really easy so we don't have to use high-powered tools. This guy, the limit, okay,